Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's weekly contest, count the number of good subarrays. The problem states that you are given a array nums and an integer k. You need to return the number of good subarrays of the num. Now the subarray is good if there are at least k pairs of indices such that array I is equals to array j, and notice that I should be less than j and they should not be equals to each other, right? So you need to figure out how many good subarrays are there, and the definition of a good subarray is number of distinct pairs of equal elements. If they are greater than equals to k, then the subarray is good. So let's take an example. Let's say this is a array and k is 10, right? So if you take the entire array, then you will say, okay, there are 10 different pairs which which are equal in this particular subarray, and hence this particular subarray is good. Now notice that any other subarray like this 4 or any other subarray will not be good, because if you calculate the number of pairs I and j such that array I equals to array j, you will see that will come to be less than 10, and hence only one subarray is good and we return 1 as an answer, right? So hope the problem statement is clear. Now how to solve this? So before worrying about any time complexity or anything, as always, I would prefer solving this in very brute manner first, and then we will look at how to optimize it, right? So we have to find the number of good subarrays, right? And subarray is defined as something L and R. Like you start with some L, and let's say you end at some R. So this is your subarray. This part is your subarray. Now you need to figure out whether this subarray is good or not. Now how will you do that? First thing, notice that you need to count number of equal pairs, like number of pairs which have equal values. So let's say, like you can see here, there are three threes, right? So with three threes, how many pairs you will get such that you like one of like I and j is one of these values, right? Like you have to figure out I and j, right? And you know I can be one of these threes and j also can be one of these threes. So let's say you can fill I with in three ways, right? Now whatever you have filled here, depending on that you will fill this part in uh, one more way. Like let's say you fill this you fill I as this L, right? Let's say I is this particular three. Now if I is this particular three, there are two possible choices of j, right? Now let's say if I is this particular 3, there are again one possible choices of j, right? And if let's say I is this particular 3, there is no possible choice for j at all, right? So what we are seeing here is the value is 2 plus 1, or in other words it is number of n into like sorry n minus 1 into n minus 2 by 2, right? Basically 1 plus 2 plus all the way up to n minus 1. So this is the value. Now you have to do this for every distinct integer here, and then you will get the total number of pairs which have equal values, and you will just simply compare that with k. And if it is smaller than k, this particular subarray is not good. If it is greater than k, this particular subarray is good. Now what is the time complexity? Again, what we are doing for each subarray, we are iterating over it and then figuring out what is the frequency of each elements, right? Let's say you iterate over this subarray, you figure out, okay, 3 has frequency of 3, and similarly 1 has frequency of 1. Now after doing this, you will again iterate over all the distinct integers here and apply this formula for the frequency, right? So what is the total time complexity for each subarray? You are iterating over the subarray, right? Iteration take order and time, and after iteration you will again iterate over distant element, that is also like order n. So this is what you are doing for each subarray, and how many subarrays are possible? N square, right? So total complexity is order n cube. if we do it in this fashion, right? And n cube will surely not pass, even n square will not pass. So let's just try to reduce this n cube to order n square first, and then we will try a next step. We'll go forward a step and reduce this n square, right? So if you are not able to reduce this n cube to n square itself, how would you solve this for order n, right? So that's how the thought process should be. Like, okay, I am able to solve this in order n cube. Now let's just see if I can solve this in order n square, right? Now, I think we have discussed this trick a lot of times in this particular channel. Uh, how to reduce the complexity if you are iterating over the subarrays, right? So one very simple trick to reduce the complexity if you are iterating or if you require an iteration of the subarray. So previously we take a subarray and we are iterating over it to calculate the uh, frequency metrics or frequency values. So if we do something that doesn't require iteration over the array, you have to iterate over all the individual L and R. Like we can't actually skip any subarray. So number of subarrays order n square still, right? Now if you have to, previously we were doing order n time, we will require order n time to, because we are iterating over the subarray, right? Now if we can skip this iteration somehow, then only we will be able to reduce this order n cube to order n square, because this n square is something we can't remove. We have to consider all the subarrays. There is no other alternative here. Like basically removing reducing the iteration here is far more difficult than reducing the iteration here. So that's why we will focus on reducing this, right? Now how to like, let's say you started with this L, right? Now every time you start with here, you will start with this particular R itself, right? Now with this L, you will consider all the all the all of the R's at once. So let's say this is L. Now you start with this R. You will keep on calculating the frequency array. Like frequency of 3 is 1, right? Now after you do this, you considered a subarray already. So just take the value of frequency here. Now after this, take this particular subarray, like you just increment R. Now if you increment R, whatever you have calculated previously will not be waste. It will be there, and simply you will increment the frequency of another element here. Now again increment R. Again, whatever you have already calculated will not be waste. You will increment R, and here the frequency would be increased from 1 to 2, right? And so on and so forth. So basically now you can see we don't need to explicitly iterate over the entire array. Rather, we are just iterating over like we are just incrementing L and R in a particular fashion, and thus that doesn't require a reiteration over the array. But there is a catch. Let's say you again we are at here and we calculated the value correctly, and let's say the value is 3, right? Now even if we reach here, there is one more thing that we need to take care, right? So this is L and R. Now we have frequency of three, but we again have to apply the formula for each of the distinct elements here, right? So for each subarray, we are not iterating over the array to calculate the frequency. Remember, there were two n's, right? First n to iterate over the array to calculate the frequency, and second n to actually iterate over the unique elements and apply the formula n minus 1 into n minus 2 by 2, right? So we reduce this by actually iterating in a specific fashion. But still we have to iterate over the distinct elements again. Otherwise, this n will not be gone, right? And our complexity would still be order n cube. Now we have to reduce this n as well. Now how to do that? Again, if we can somehow reutilize whatever we have, we will save us from again iterating over all the distinct elements, right? So think of it like this. Let's say you previously R was this, okay, and if R is this, the value of this frequency would be 2, right? Now let's say you incremented the R to this. Now if you incremented the R to this, you will be incrementing only one value from here, right? And if you are incrementing only one value here, why are you iterating over all the distinct elements? Right? That's the key. We are only touching one value in this frequency map, but we are reiterating over the entire frequency map to figure out or to apply that formula and figure out the number of distinct pairs which are equal. But because we are only caring about this value, we can simply remove this. And by removing, I mean, let's say previously the number of pairs is p, number of distinct pairs is p. Now, what you do, you will just subtract the contribution of 2 from here and add back the contribution of 3, right? That would do, right? Basically, we are incrementing 2 to 3. So, whatever contribution 2 had made, we'll subtract that completely. So, it is like there is no 3 at all. And then we add back the contribution where there are 3 number of 3's. So, hope this makes sense. Like this is still order 1 operation, and we can reduce this order n to order 1, right? So finally, this iteration doesn't require anything, and this is also order 1 now because we are just subtracting something and adding something. So this entire operation is order 1. So we will get the number of distinct pairs p, which denotes how many distinct numbers or how many distinct pairs are there which have equal values, and that's what we want. And for each of these subarray or for each of these L and R, we have the P and we just compare it with K, and based on the value we will increment or decrement, right? So hope this thing makes sense. Now like just now we have reduced our n cube to order n square, right? Now what we are doing, simply we are starting L from 0 and R from 0, and we are keep for each, like keeping the L fixed, we are incrementing R up till n, and then we are incrementing L and then again resetting the R, and then again incrementing L to the end, right? So this is what we are doing, and that's what our complexity also suggests, like order n square. Now I would encourage you to code this yourself if you are seeing this kind of optimization for the first time. That would actually help you grasp this even better. Now, once we have reduced this entire thing to order n square, we need to optimize this order n square to order n, right? Or n log n or something like that, right? So there are only a few possibilities. So notice that you have to iterate over one of these L and R, right? So the best thing is to just iterate over L for now. Now, if you are iterating over L, this R is something for each L. You just need to put the R at a point where you will see, okay, or in other words, you don't need to iterate, you don't have to iterate the R to all the indices. Instead, you will say, okay, given this L, tell me how many good subarrays are there starting at this particular index L, right? Now, there are a handful of techniques that you can apply here, like because you know the you have to calculate the value in terms of subarrays. You have to bring in R. Now, once you bring in R, you can't actually iterate R as well. Like let's say you start R from here, and then you think, okay, after starting from here, I will iterate over the rest of the R, rest of the indexes. Even that is not possible. So basically, you have to remove R at all from the picture, right? So there are a couple of choices here. First thing, you can see if R is strictly increasing or not, right? So let's just remove these things. So you can just see whether R is strictly increasing or not. If it is strictly increasing, we can apply 2 pointers, right? And second thing is, if R, like if we can binary search for R, right? Let's say we binary search for R and we say that, okay, this is the first subarray. This is the first subarray which is good. And because this is good, every other subarray is also good, right? Because this is the first point where the subarray becomes good. So every other subarray would be good by itself, right? Now, depending on like as we mentioned, like there are two possibilities. Either we can see if R is strictly increasing, or we can see if we can binary search for R. Let's this binary search is not applicable here. The reason being, let's just first discuss this. So the reason being, let's say, okay, first of all, I assume that you know what binary search is, and if you haven't, aware, or if you aren't aware of how to think of whether binary search is applicable in a particular problem or not, I would strongly encourage you to check my other video out. I will link them somewhere in the comment section or in the I section on the top. So here binary search is not applicable because for any r, like if you put r at particular index, let's say this index I, you need to decide whether you can you have to deterministically decide that whether you can go left or right. So going left or right is something you can decide definitely without any issues. But the condition is something which is not in our favor. In other words, to calculate anything at that particular index I, we have to then iterate over all the distinct elements. This frequency array, let's say we build somehow, right? But even if we build frequency array, we have to iterate over all the indices. Now, why all the indices? Because just before we have noticed that calculating frequency array is not enough. We have to iterate over all the indices for or all the frequencies to get the actual number of pairs. Now, to get like if you iterate over all the frequencies, that would require order and time. So even binary search would not help here, right? Or it will make the things work worse, right? So we can't apply binary search. So we can see if R is strictly increasing. Now, why? What does it mean that R is strictly increasing? It means that let's say for this L, this is the first R where everything becomes good, or this is the first R where number of distinct pairs is becoming greater than equals to k, right? Now after this R, every other array would be good, right? That we already know. Now for this L, we stop at this R. Now let's say we increment our L to this. Can we say that R would be somewhere afterwards? It will never come back. If we can say this, it means R is strictly increasing. And if R is strictly increasing, we can simply apply 2 pointers and solve the problem. This is the best thing that you can get in any problem. Like if R is strictly increasing, simply apply 2 pointers and that would solve the problem. In this particular problem, R is indeed strictly increasing. Now, why R is strictly increasing? Let's say there are k pairs, like there are p pairs from when L is this, right? There are p pairs, and this is the first index. This is the first index where p becomes greater than equals to k. Now if p is greater than equals to k at this particular index, if we increment L, can p be greater than equals to k at anything before this? Answer is no, because if it is the case, then this particular condition would also be satisfied. So let's say you are saying that okay, if I bring L here and I can have R here, it means that if this is valid, then if L is here, then this part will also be a valid subarray, because you are not removing anything, you are instead adding some elements. So adding some elements would not deteriorate anything, it will just improve your number of pairs. So because this L and R is not valid, this is the first R for this L, hence we can say if we increment L, we will never decrement R by any chance. So the valid value of R would always lie afterwards, and because that is the case, R is strictly increasing here, and we can apply 2 pointers. So simply what we will do, we will start L from here, right, and R from here. For this L, we will keep on incrementing R until we get the first good index. Once we get the first good index, again, how to get the first good index? We will keep on maintaining this frequency array, and we will keep on doing that trick, like p minus contribution of previous frequency and addition of new frequency, right? So we'll keep on doing this trick, and once we found out that okay, this is the valid R, we know for this L how many distinct subarray are possible, right? Now we just increment R, and after incrementing R, we will decrement the contribution of this again. So notice that here 3 is now decremented to 2 again. So we'll just decrement the contribution of 3 and increment the contribution of 2. Now after this, we will again see if p is not if p is less than k, we'll keep on incrementing R, and let's say this is the good value here now. So if in this case we will say, okay, there are like number of subarrays would be one of like one subarray is this, another subarray is this, right? And so on and so forth. So that's how we will keep on incrementing R, incrementing L, and R will always be increasingly. So hope this point makes sense. Let's look at the code that would make things a bit more clear. As we discussed, we have two pointers L and R. We maintain the frequency, and because we both like they are both pointed to zero, we will just increment the frequency of zero right away. We have a pairs. Initially, pair is zero because with one element there can't be any pair formed, right? After that, we will like we will just see we will try everything for all L. So initially L is zero, and then L we will keep on doing this until L reaches to the end. So for each L, we will keep on incrementing R until pair less than K, and R can also be incremented. So until pair is less than K and R can also be incremented, we will keep on incrementing R. And notice that what we are doing, we will also keep on maintaining our frequency uh, map. So we calculate the frequency map, and also we have to uh, apply this formula P minus contribution of previous frequency plus contribution of new frequency. So this is just a smaller version of that formula. Like if you just subtract this two value, you will get something like this. So this implementation details. Now, if pair is greater than equals to k, you will just simply add result plus equals n minus r. Now why n minus r? Like this r is, let's say this r is the first value. So if this r is the first value, this subarray and everything after that will be valid, right? So there are like n minus r such subarrays are there. So hence you incremented your answer by n minus r. Other after that you will just decrement the frequency, like you just have to increment the value of L, like you will just increment L. Now before incrementing L you have to decrement the frequency of previous value of L, and also remove his contribution from the P. So that's what we have done. We calculated the frequency, we remove his contribution from pairs, and then we simply incremented our L. So we'll keep on doing this, and finally we'll have our result. So hope it makes sense. If you have any doubts in this problem, please post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.